Hello everyone, Dr. Data Science here to teach you data science methods and tools today, tomorrow, and beyond. This is the third video in the Machine Learning with Imbalanced Data series. In the first two parts, we examined the class imbalance problem where the number of samples or observations belonging to one class is significantly lower than those belonging to the other classes. For example, in medical diagnosis studies, such as the Thyroid dataset, imbalance classification is a common challenge. To learn from imbalanced data, we discuss proper evaluation metrics, such as precision and recall, and we also explained one approach to alleviate the problem known as cost-sensitive learning, where we modify the loss function to take into account that the cost of a false positive and a false negative may not be the same. In this video, you will learn a new technique for addressing the class imbalance problem and how to apply this technique using an open source Python library known as Imbalanced-learn. To start, let's take a look at the three main categories to tackle the class imbalance problem. The first one is data level preprocessing, which operates on the training dataset and it changes class distributions using resampling techniques. Therefore, these methods aim to alter datasets in order to make standard machine learning algorithms work. That is, in contrast to cost-sensitive learning, we don't modify loss functions because of the preprocessing step. An important direction in data level preprocessing is to generate new samples in the classes which are underrepresented. This approach is known as oversampling, and the simplest way is based on uniform sampling with replacement. Therefore, this allows us to balance the input dataset before the training stage. We again work with the Thyroid dataset, which consists of 3,772 patients, and only about 6% of these patients are classified as positive or +1, and the other 94% of samples are labeled as negative or -1. If you want to find more information about this dataset, please refer to part 1 of this series. Here we name the data matrix or feature matrix as X, which is a two-dimensional NumPy array. And the targets or labels are stored in a one-dimensional array called Y. After importing this dataset, it is time to divide the data into training and test sets, where we use scikit-learn, built-in function, train test, split. As expected, we see that only 5.8% of training samples belong to the minority class. To oversample the minority class, we used the Imbalanced-learn package that you can download from the URL here. After importing this library as Imbalearn or Imblearn, we use random oversampler to randomly select samples from the minority class to rebalance the training dataset. Looking at the distribution of classes in Y trained sampled, we see that the number of samples in positive and negative classes are exactly equal. Therefore, we have a 1-to-1 ratio. To show the effectiveness of oversampling, we train a logistic regression classifier using the original training dataset and the oversampled version. As we see, the main difference is in the training stage, where we have to use the relevant training datasets in each case. We then plot the confusion matrix for test samples, and immediately we can see the advantages of oversampling. On the left, we see that if we don't use oversampling, only 43 out of 78 positive samples are correctly classified, which gives us a recall value of 0.55. However, pre-processing the training dataset will lead to a more reliable classifier where 68 out of 78 positive samples are well classified. Therefore, the recall value is increased from 0.55 to 0.78, which is substantial for applications where predicting positive classes is essential. If you want to know more about the definition of precision and recall, please again look at part 1 of this series. That's where we discuss about precision, recall, and confusion metrics and how you can use Python to calculate these quantities. Now we talk about other oversampling techniques. Instead of applying a simple replication of the minority class instances, the key idea of SMOTE, which stands for Synthetic Minority Oversampling Technique, is to introduce new synthetic or artificial examples. This new data is created by interpolation between several minority class instances that are within a defined neighborhood. To explain this approach more, the total amount of oversampling is an integer value that we give to the algorithm, which can be chosen to obtain an approximate one-to-one class distribution. Then an iterative process is carried out composed of several steps. First, a minority class instance is selected at random from the training data set. So that's what the xi that we show here. Next, its k nearest neighbors, which here we set k equals to 4, are obtained. And finally, n of these k instances are randomly chosen to compute the new instances by interpolation. This technique is very popular in machine learning, and as you can see from the reference here, SMOTE has originally introduced about a decade and a half ago, leading to a multitude of oversampling techniques. To apply SMOTE to the thyroid dataset, we again use the Imbalanced-learn library that we imported as Imbalancedlearn, and this time we import a SMOTE instead of random oversampler. This will give us a one-to-one ratio of class distributions in the training dataset. And similar to the previous example, we use the pre-processed data, which is the X-train sampled for features and Y-train resampled for labels, for training a more reliable classifier. As we see here from the plotted confusion metrics, SMOTE is able to significantly reduce the number of false negatives, such that out of 78 positive samples, only 11 of them are labeled as negative. I hope you found this video useful. In the next one, we will talk about undersampling techniques. I want to thank you for watching this video.